Okay, this is Dr. Williamson working on a reaction rate problem. And here I have for the reaction A goes to P products, and it's 1-to-1 stoichiometry. I have A, concentration of A versus time is plotted. How do you determine the following? Little a, the average rate over the entire reaction. B, the reaction rate at time t. C, the initial reaction rate. And D, would you get different results for all of the above if you plotted P versus time, why or why not? Okay, so let's get the average rate over the entire reaction. Over the entire reaction, you would calculate that the rate would be equal to minus delta A, delta A over delta T for the entire reaction. So that'll be minus concentration of A final. That's supposed to be square brackets. I'm writing with my mouse, so this is sloppy. Concentration of A initial over T final minus T initial for the entire reaction. In this case, it'll be minus final concentration. That looks like I have to estimate this. Let's do this. Let's draw. And if I estimate this, I'm going to draw a line here. I'm going to have to estimate this. Right about here, this is 5. That looks like 2.5. So this looks like half of 2.5. So half of 2.5 is 1.25. That looks like half of that so that's about 0.625. So I'm going to guess that that is about here, and it's a rough guess, it's about 0.5 or so. Okay, so I'm going to go 0.5. And what time index was that at? 100 seconds. Minus the initial 5. These are units of molarity. Minus 0 seconds. And the question was, how do you determine it? Not so much get the correct number. So I'm showing you how to determine it. So if you estimated the 0.5 slightly differently, that's really not what's critical here. What's critical here is I'm showing you the skill on how to get it. So if I go ahead and do that, that's going to be 0.5 minus 5 divided by 100. And then I have another minus sign. That'll be positive 0.045 molarity per second, which is the same thing as moles per liter per second. I'm not paying real close attention to sig figs right here because I'm showing how to determine it. And so I wasn't being real careful with sig figs when I set up the problem. I guess I could make this 3 sig figs if I wanted to. Okay, but you guys get the idea. That's how we determine the average rate over the reaction. Okay. Now, how do we determine the reaction rate at time t? I'm going to keep this up, but I'm going to erase this. Determine the reaction rate at time t. I'm going to erase this also. Okay, get rid of that. Get rid of that. Oops, I want to keep that. Yeah, I want to keep that. Nope. I'm going to erase this. There, oh, that worked. Okay. What I need to do is I need to draw a tangent line right at this point right here. I need to go straight up to here and draw a tangent line right to that point. So I need to draw a tangent line right there. So let's do this. Let's draw a tangent line. That looks fairly tangent right there at that point. Okay. And then what I'm going to do is take 2 points off the tangent line. And so I'm going to take, let me change the colors here. I'm going to take a point right here off that tangent line and a point right here off that tangent line. And we're going to call this a initial, whatever value that is. And this, draw straight down to be T initial for this tangent line. And this will be here, go straight over, don't do it crooked like I'm doing. A final. And this would be T final. Whoops. T final. Right? And I would put those numbers in. And so the rate would be minus, and then whatever A final was, whatever number I picked off of there, I would put that right here where that was, whatever number that happened to be, minus A initial, whatever number I happen to estimate that to be. That looks like that might be close to 2.5, right? Because it's halfway up to 5. And then this looks like this might be close to 50 seconds because it looks like 0. That's 100. So 50 might be right about here. So maybe that's about 40 seconds. So I would put whatever time that was there. It might be about 40 seconds. That's not critical to what we're doing here. And whatever final concentration that was, right? Oh, excuse me, I already put that there. And whatever initial time that was, I would put that there. Okay. So what matters is when I'm getting the time, when I'm getting the rate at a specific time, I draw a line straight up at that time. Then I draw a tangent line. Then I take 2 points off the tangent line. What I do not do is draw a line straight up and then take 2 points off the curvy line on either side. You don't do that. You draw a tangent line. Okay? Draw a tangent line. Okay, that's how you do that. Let's see now if I can erase this stuff successfully. Okay. Well, how do you get the initial rate? Okay, do the exact same thing to get the initial rate, right? I need to move this stuff here. I'm going to move that stuff out of the way. To get the initial rate, all I do is, instead of drawing a tangent line at this time t here, I draw a tangent line at time t equals 0 seconds. So what I'm going to do is mentally extend this curve the way that it looks like it would extend. Right, if I were to extend this blue curve, it looks like it would continue on the way that I've already drawn it right here. That looks kind of natural right there. And then I would draw a tangent line to that. Make sure it's tangent. In other words, it only touches at time t equals 0. That looks tangent. Then I'm going to take 2 points off of that tangent line. I'll take this point right here. Whoops, that's not what I want to do. Let me do this. Take this point right here. Take a point right here. So this will give me a initial and time initial, right? A naught, excuse me. And this will give me a final versus T final. And then I just plug the values into here and I'll get the reaction rate at time t equals 0, which is the initial reaction rate. Okay, right at, not an average reaction rate, but the instantaneous rate right at time t equals 0. Okay, that's how you do that. Erase this stuff. Okay. Then the next question is, whoops. Would you get different results for all of the above if you plotted t versus time, y or y not? No, you would get the exact same results. The reason for that is because here, if I write down the definition of rate, the rate will be equal to minus delta A over delta T, which will be equal to positive delta P over delta T. And it's one-to-one stoichiometry. And this minus sign takes care of the fact that A is decreasing in concentration. So the stuff inside the parentheses will be negative. So this minus sign gets rid of that negative. So you're going to end up with whatever number you get here. If you were to plot P versus time, you would get a plot that did something like this. And if you were to graph P versus time, you would get whatever number you got here, you would get the exact same value as if you did A versus time. Okay, you're going to get the exact same values. Okay. Anyway, I hope that helps. And, I'll try and do some more for you guys later.